All right, welcome to calculus. We're going to look at average value. Now, the idea of average is something that's been around for quite a while. It's been used in lots of different ways and different purposes, and it has a lot of usefulnesses to us. One of the things we want to think about when we talk about averages in terms of integrations is really paying attention to what integration means. And I have said this before in everything, and when I first introduced integrations, is integration is a total of some sort. Okay, that is its most basic definition. If you think about the mathematical definition of an integration, it is the limit of a summation. The limit as the number of pieces, the number of subpieces, the number of subintervals that you're letting the space or whatever be split up into is going to infinity. So you're summing up every single piece on a given interval. So what you're really doing is you're totaling everything up over a interval. That can be very useful to you in lots of different respects. We're going to look at a couple of little pieces here that might help us understand what we're talking about. Now, one piece of this is this idea that when we talk about finding an average over an interval, maybe the average speed or the average anything, really all we need to do is find the total and then divide by that space. So let's take this example. Let's say f of x in this particular problem, but maybe it doesn't have a whole lot of meaning, but I'm going to work through another one here that does in a second. Let's just take f of x. All right. And let's just, for right now, let's just define our domain here. And I mean, of course, it goes the other direction as well. It's a horrible drawing. But let's just define our domain here for x to be greater than or equal to 0 and less than or equal to, say, 3. Okay, and these numbers may not work out very nice, but that's okay. So we're only talking about a very small portion of this curve, namely this little section right here. Now, I purposely drew it in that way because what we're really doing on this is if we're wanting to find the average, say the average position between x equal to 0 and x equal to 3, what we need is the total position on that interval and then divide by the interval itself. So even if maybe it might make more sense for us to go from 1 to 3, just to kind of emphasize what we're doing a little bit better. So let's just go from 1 to 3, okay, because that will help us understand a little bit more what we're doing here. So we're going to start the interval right there. We're not even paying attention to that, so we're just dealing with this little section right there. What's the average position? Now, think about when this might be useful to us. We're talking about what is the average capacity for a bridge, or the average number of people that are on the bridge. What does that look like? There are all sorts of different ways this can be used, but really ultimately what we need to do is we need to integrate from 1 to 3 of x squared dx, and then we're going to need to divide by 3 minus 1, right? Another way we could write this is 1 over 3 minus 1 times the integration from 1 to 3 of x squared dx. Now notice how the 1 and 3 on the integration here match up with the a and b inside of this value or the denominator there, okay? So we end up with 1 over 2 times that integration, and that's going to be x cubed over 3 evaluated from 1 to 3, right? So that is 1/2 of 3 cubed over 3 minus 1 cubed over 3, and then whatever that works out to be. So is that a 27/9 minus 1/3 and half of that? So maybe it's easiest to write that as 26 over 3 times 1/2, so that'd be 26 over, say, 6. All right. And of course, there are probably some reduction we can do here, but this would be the average position, average amount of money made. Maybe this equation describes the profit over a time interval, so this is the average money made. There's lots of different ways we can look at this. Now, there's another aspect of this that is kind of really fun to look at is the idea between volume and position. And what I'm actually going to do here, and I think only because I think this is a fun little process to think about, is to show that the average velocity over a time interval is the same as the average velocities during the trip itself. Now, what I mean by that is, let's think about the integration from of v of t. V is velocity, right? So, and let's just go from time A to time B. Okay, and it doesn't really matter what values we're using here. We can use t's if you want to talk about this in terms of time. All right, so what are we really talking about here? The integration of velocity is position. So what we found is the position, or how much distance, how much displacement has occurred in that time interval. So what this is the positional change from x equal to a to x equal to b. That's what we found there when we did that integration, right? Now let's just take that integration. Let's just say, let's find the average velocity. Okay. Well, if we want the average velocity, we're going to do 1 over b minus a times the integration from a to b of v of t. So whatever our velocity equation is over that time interval, right? Now, what is v of t? Well, v of t is the first derivative of position, right? So if we think about this being first derivative of position, what we're really dealing with is 1 over b minus a times the integration from a to b, right, of s prime of t. S prime just being another way to write v of t. Well, what is integration and derivatives? They kind of cancel each other out. So the integration of the first derivative of s is going to be s. So now you have 1 divided by b minus a times s of b minus s of a. Now, if you want a little bit of side work on that, the idea is that we're integrating this. I'll kind of do that off to here. This little piece right here, that turns into s of t evaluated from a to b, right? Which turns into that little part right there. Well, what are you dealing with at that point? Well, now what you're dealing with is s of b minus s of a over b minus a, which, by the way, is the definition for slope, right? And what we just found there, all right, if position, think about this from an equation standpoint, or from a position. So here we have our position, strike that. Here we have our time, here we have our position, right? So here is A, here is B. Here's this position, here's this position. What did we find? We found the slope between those two locations. So that is the change. What we did was the change in position divided by the change in time. By definition, that is velocity. All right. So if that is velocity, and in fact what we found was the average velocity between those 2 points, that's the secant line, right? And think back to when we do derivatives, what we're finding is the instantaneous rate of change at a point. So what we found here is the average rate of change between 2 points, because it's the secant line, right? So we're not finding the instantaneous rate here, we're finding the average between those two locations. So here is just another example of how this average position, which in this case is actually the velocity, right? It's the average velocity over a given interval, and how these two pieces interact with that. I just think this is a neat little one to look at. If you need more examples on averages, average value, just remember that it's just taking the equation, integrating, and then dividing by the width of the interval, okay? If you need additional examples or problems on this, or additional examples to go by, please reach out and I will post those as best I can. Take care.